In this video, we will have a closer look at some of the properties of tensors. We will discuss different types of tensor components, ways of combining tensors into new tensors, and the tensor derivatives. Starting with the tensor components, the components we saw in the previous video were the contravariant tensor components. When we discussed vectors, we introduced the covariant vector components, which were constructed by contracting the contravariant components with a metric tensor, and denoted by a lowering the index. We also saw that this leads to the covariant vector components transforming in the same way as the basis vectors did under Lorentz transformations. In addition, the inner product could be written in terms of the covariant and contravariant components of the vectors, always making sure that we have one contravariant and one covariant index when summing. We can apply exactly the same construction to tensor components, and we define the covariant tensor components with the indices down, lowered relative to the contravariant vector components by multiplying with one copy of the metric tensor for every index. The same type of argumentation that led us to the transformation rule for the covariant vector components will now lead us to the transformation rule for covariant tensor components. As for the contravariant components, we get one factor of transformation coefficients for each index, but now of the inverse transformation rather than the transformation itself. Unlike in the case of the vector, which only has one index, we may choose to only lower some of the indices of a given set of tensor components. When we do this, the resulting tensor components are neither contravariant nor covariant, and we refer to them as mixed tensor components. Note that in this case, we have lowered the first index of the tensor t, which is the index that is summed with an index from the metric tensor. There are a number of ways of composing new tensors out of ones you already have. The first such example is the outer product. In fact, we already saw this construction when we introduced tensors by taking the outer product between two vectors. However, the construction is more general, and writing out the tensors t and s in component form and using the bilinearity of the outer product, we obtain a new tensor that has the product of the components of t and s as its components. In this case, we took the outer product of a rank 2 tensor with a vector and obtained a rank 3 tensor as a result. Another way of creating a new tensor from a tensor of rank 2 or higher is called contraction, and the result is a tensor of 2 ranks lower. The components of the contraction are defined by summing two of the contravariant indices of the tensor with the indices of a metric tensor. Since summing with a metric tensor is also what makes an index covariant, we can also write this contraction in terms of the mixed tensor components of t. Note here that when doing so, we will still have one sum left. In this case, the sum over mu, as compared to the two sums on the left-hand side. The resulting object in this case has one index and is therefore a vector. This is true as long as the components transform in the correct way, making the definition independent of the basis we used, and so we need to check this. By writing the same definition using a different basis, we can write down how the components in the primed frame relate to those in the unprimed one. Since we have a sum over mu prime, we can here use the fact that the factor which multiplies the covariant contravariant indices are each other's inverse, and taking the sum, we end up with a delta. Summing over nu, this delta allows us to replace the nu in the unprimed component with mu, and the resulting transformation rule for the contracted component is exactly the transformation rule expected from the contravariant components of a vector, with a single transformation coefficient. Combining the outer product with the contraction of an index each from the original tensors, we get the inner product. Note that the inner product can be written in terms of covariant or mixed components, as long as we make sure that there is exactly one contravariant and one covariant index for each sum, and as long as we have the same free indices on each side. An important feature of equations involving the components of tensors in any given frame is that the form of the equation does not depend on the basis we have chosen. If t mu nu s mu is equal to v nu in the unprimed frame, then t mu prime nu prime s mu prime is equal to v nu prime in the primed frame. This is true for equations with any number of free indices, But in particular, when there are no free indices, we have a tensor of rank 0, which is just a scalar, a number that takes the same value in all bases. Finally, let us make a comment regarding the gradient of a tensor. From vector calculus in Cartesian coordinates, we are used to the gradient of a scalar field being equal to a vector with the partial derivatives of that scalar field as its components. The question we ask ourselves is, therefore, how the partial derivatives transform under coordinate transformations, and whether or not this will allow us to identify the partial derivatives of tensor components with the components of a new tensor. By the chain rule, we know that the partial derivative with respect to x mu is equal to dx mu prime dx mu multiplied with the partial derivative with respect to x mu prime. And already here we have the transformation rule. We have just related the partial derivatives in the different frames with a set of transformation coefficients. This tells us that partial derivatives transform covariantly, which also justifies our placement of the index in down position. In particular, if we take the derivative of the contravariant tensor component t nu sigma with respect to x mu, we can rewrite everything in terms of the prime partial derivative and the prime tensor components. Since the transformation coefficients are constant, we can move them out of the derivative. And we are left with the exact transformation rule for a tensor with 2 contravariant and 1 covariant index. This concludes our tensor primer for special relativity. I hope what has been covered here will help you navigate the jungle of indices flying up and down that you will encounter when studying relativity.